Hello everyone, welcome to my YouTube channel. Today we are going to study about current electricity. So what is current electricity? I hope you all have experienced current electricity. So before understanding current electricity, you have all experienced while touching any switch with wet hands, while touching to see whether the water is hot or not, while an immersion heater is dipped in and the switch was plugged on. Remember, you have all experienced what is current. So basically current is of two types. One is AC current and one is DC current. Now this chapter is all about DC current, and yes, in class 12 you do have to study AC current as well. Yes, I am going to explain to you everything regarding AC current later, but let us complete this DC current chapter first. So what is DC current? When current flows in unidirectional motion, that is DC current. So let us get into this chapter, what it says. So before going to my chapter, do one thing, just press that bell icon and a red subscribe button. Yes, you will be able to understand physics much better if you do this right now. So okay, let us understand this first. So till now we have all studied how much charge is present in a body, that is how much charge can apply force on another charge, whether it is positive charge or negative charge. We have understood everything regarding that. What is the potential difference between the two bodies? What is the potential due to a charged conductor? How much charge should be given to a conductor to get a desired electric field? So you have already got knowledge of electric field, electric potential, potential energy of these things. But in all these cases, remember, these charges are in static position. These charges were not moving. They are all in static position, that is they are given in a body, and these charges are in that position only. So there is no question of moving charge. So here we are going to understand for the first time in this current electricity chapter that the charges are in motion. So we have studied electrostatics where the charges are in static position, and here we are going to study about electric charge that are moving in motion. This motion, yes, this motion of electric charge is going to give you electric current. So how electric current we are getting? What is the reason for this charge to go in motion to create this electric current? We are going to understand everything in this video today, right now. See why electric charge flows. Suppose here I place a conductor, this is conductor A, and I have given some charges to this conductor. So this conductor has gained some charge. As a result of gaining charge, its potential, its electric potential also increased, right? Now another conductor, if I place another conductor B, here also it has some charge. So here also it has gained some amount of electric potential. So this conductor has electric potential, suppose VB, and this conductor has electric potential VA. Now if I say VA is greater than VB, now if I say VA is greater than VB, then it is clear that this has more amount of charge, this has more amount of charge, provided these two conductors are similar. So if I connect a wire between these two bodies, then what will happen? The charge starts flowing from conductor A to conductor B. As these charges are flowing from conductor A and conductor B, this flow of charge is giving rise to current. So what gives rise to current? The flow of charge that gives rise to current. Why the charge flows? If and only if there is a difference of electric potential between two bodies. So here the charges are flowing through a conductor because conductor conducts electricity. We are going to understand all these things later. Why conductor conducts electricity, why not insulator. You have some idea about this, but still we are going to understand those things later. But now for this moment, just keep this in mind that there is a difference in potential between conductor A and conductor B. This difference of potential is giving rise to electric current. So difference in potential, difference in electric potential gives rise to flow of current, that is flow of charge. Flow of charge, right? So this flow of charge is giving rise to current. Now if you are still having any problem why this charges will flow from conductor A to conductor B in spite of having greater potential at this point and lesser potential at this point, just think of the basic idea. I have that explained in the capacitor chapter. Think of the basic idea. Suppose if I connect two bottles, one bottle's level is up and the bottle level is down. Now if the bottle is connected, then what will happen? The water will flow from higher level to lower level, right? Higher level to lower level means that is from higher potential to lower potential. That happens, right? That is quite clear to everyone, right? So here is what happening. Charges are flowing from high potential to low potential. This flow of charge is giving rise to current. So this is clear to everyone. So now we are going to understand in an electric circuit what happens. So come, let us understand that part. So here we can see this is a battery that is connected to a wire to this resistor. So this forms a closed circuit. Now here what is happening? Here current is flowing. Now how current is flowing? Let me tell you by step by step. Here this electrode of this battery, or this terminal of the battery, which is here I have marked as positive, this is at higher potential and this negative is lower potential. So battery has two terminals, one is positive and another is negative. If you don't know, just check out the battery that is inside your remote. Okay, so battery has two terminals, one is positive and one is negative. So positive means high potential and negative means low potential. Now what happens here? Electric charges from high potential, that is electric charge, that is positive charges from high potential will always try to flow towards low potential. Just now I have told you. So electric charges from high potential tries to flow from high potential to low potential. So in this process the electric charges flow. Now this flow of electric charge gives rise to current. So what current can be defined as? Current can be defined as the rate of flow of charge. Defined as rate of flow of charge. So rate of flow of charge means how much amount of electric charges are passing or flowing per unit time. That means within how much time, how much amount of current is passing. So we can say current is I as total charge. Suppose total charge passed within total time. So current can be defined as like this. How much amount of total charge is passing in how much amount of time. That is why I am telling is rate of flow of charge. Using calculus method or differential method, we can also write like this. I is equals to dq by dt. dq by dt means how much amount of charge, that is dq amount of charge moved within dt interval of time. So in a simplified term, I can be written as del q by del t also, but in differential term we can define I as dq by dt. So this is clear. So why current is flowing? Why suddenly current is flowing? Because there is a flow of electric charge. And how this electric charge comes to flow? Because there is a change in potential difference. Now imagine this scenario, what is happening? This electric charges are flowing from high potential. These electric charges are flowing from high potential. Now when it flows through the resistor, its potential gets dropped and then it returns back to the negative terminal of the battery. Now what is happening here? Battery is doing some work again to bring those charges from negative terminal to positive terminal. How the battery is doing these things? The battery is doing these things using electrolysis. Yes, you will be going to understand electrolysis in your chemistry classes. But yes, battery is doing electrolysis to bring these charges from negative terminal to positive terminal. And this in turn helps to flow the charge in this circuit in a continuous way. See, this charge is flowing in unidirectional. This unidirectional flow of charge gives unidirectional flow of charge give rise to DC current. DC current. I told you current are of two types. One is DC current and another is AC current. So here you see this unidirectional flow of charge give rise to DC current. So we have got to find out, we have got to understand a bit knowledge of DC current, right? So this is what is happening in a circuit. Now if even also you are having any problem to understand this, imagine a child playing in a playground. Now she or he observe a slip. What you know what is slip, right? So what she does, she goes to the park and she goes near the slip, and what she does, she climbs up the stairs and then she releases herself. So she slides down through the slip. Again what she does, she again goes and climbs the staircases and again slides down the slip. So what is happening over here? This work done by the girl or the boy to climb the slip or to climb the staircase of the slip is the work done by the battery. This is actually the work done by the battery. This battery is doing this work to move the charges from lower potential, that is lower potential here, the negative term is lower potential, to higher potential. The battery is doing the work to move from lower potential to higher potential. So similarly here also this child is doing some work to move from lower potential to higher potential, and when she releases herself, she moves through the slip. Now this movement, this flow of this child can be understood as current. So what it is happening here, these charges are also facing the same thing. They move from lower potential to higher potential, and then what? They just releases themselves. Why? Because they are going to flow in this direction. Why? Because charge always flows from higher potential to lower potential, and that is the thing, how current is flowing through the electric circuit. So let us find out what is the unit of current. So SI unit of current is, see, current unit can be referred to as, you can understand from here, coulomb by time. So it can be written by coulomb per second, but we name this as ampere. We name this as ampere. So SI unit of current is, SI unit is of current is ampere. So we have got this, SI unit of current is ampere. So there are other units of current also, that milliampere, microampere, also sometimes kiloampere. So there are other units of current also. So 1 milliampere is equals to 1 into 10 to the power minus 3 ampere, and 1 microampere is equals to 1 into 10 to the power minus 6 ampere. So these are the other smaller units of current. So these are the other smaller units of current. I hope you have understood this part. I would request you to write it down in your copy. If you have any problem, you can, as always I have told you, write me in the comment section. Now what happens when you connect a battery to a conductor? First let us understand this part. Suppose this is a conductor. Suppose this is a conductor. Now what we have done, we connect a battery to this conductor. Now we are going to understand deep inside the conductor what is happening. Now we are going to understand this part. What happens as soon as we connect the battery to this conductor, what happens? Electrons, there are free electrons in the conductor which helps to flow current through the conductor. So a conductor has free electrons within them, which in general does not have net movement in any direction. So the free electrons in conductor does not have any net movement. Just understand the term net movement. They doesn't have any net movement in the conductor. So when we connect a battery to this conductor, what happens? All the electrons inside the conductor get attracted to these electrons in the conductor. These electrons in the conductor get attracted to the positive terminal of the battery. So all this electron tries to move in the positive terminal of the battery. So as this free electrons tries to move to this positive terminal of the battery, what is happening? These electrons are moving towards the positive terminal of the battery. Battery in turn, what it does, it forces these electrons to move to this negative electrode. Now when this battery forces these electrons to move to this negative terminal of the battery, then what happens, this electron again comes and flows in this direction. So what happens, this battery is trying to move these electrons in the negative terminal of the battery, and from here this electron doesn't want to stay in the negative terminal of the battery. They are always tries to move towards the positive terminal of the battery. As you know, negative charges attract positive and positive attracts negative. So this batteries doesn't want to stay over here in the negative terminal. What they does, they tries to move through this circuit, through this closed circuit, and here and comes to get over here in the positive terminal. Now battery does again the same thing. They tries to move this electron again to the positive terminal. As this battery pushes them to the positive terminal, and this again let these electrons to flow in this way. So this comes out to be in a cycle. Now ultimately, if you are asked how in which direction these electrons are moving, yes, the electrons are moving in this direction. The electrons are moving in this direction. This is the way the electrons are moving in the circuit. So this is clear. Now electrons are negatively charged. Electrons are negative in charge. So I have explained to you that current is the rate of flow of charge. Then which charge is moving? Actually these negative charges are only moving. But current is in which direction? So by convention we understand, we say current moves in the direction in which positive charges move. So by convention we understand that electric current moves in a direction where positive charges are moving. Now where is this positive charges is coming? Here only the free electrons are present in the conductor. Then how come you are talking about positive charge? This question may come into your head right now. But listen, I have told in my previous videos also that if I take some negative character out from you, then you are going to gain some positive character. So I am just taking out of negative character from you, that you are gaining some positive character. Now if a person says, then I am imposing or I am pushing some positive character in you, that person is not wrong. From his perspective, he is also correct. So taking out of negative character can also mean pushing some positive character in you, right? This is clear. So similarly, if electrons are moving in this direction, I can say positive charge is moving in opposite direction. So electrons are moving in this direction can also mean positive charge is moving in this direction. See, again I am giving you another example. If I take some amount of electrons from a body, the body gains positive charge. So am I giving some positive charge in it? Yes, the body is gaining positive charge. But am I really giving any positive charge in this body? No, I am just taking out the negative charge from it. So taking out of negative charge automatically reflects some positive charge in them. So if a person says, if a person doesn't know anything, and if a person says that this man or this person has given some positive charge into that body, then that person is correct. He or she cannot be told totally untrue. Similarly, in this similar convention, in this similar way of thinking and perspective, we understand that as electrons are moving in this direction, in this anti-clockwise direction, these electrons are moving, we are going to understand that electrons moving in this side ultimately leads to positive charges moving in this direction. So current is in the direction of movement of positive charge. So current is flowing in the direction of positive charge flow. So current is in the direction of positive charge flow. So I am thinking that positive charge is flowing in this way. So I am considering positive charge is flowing in this way, and so by convention this electric current, this conventional electric current, this is flowing in this clockwise direction. So this red arrow signifies the movement of current, that is our conventional current in this direction. So I hope this part is clear to everyone, how this current is moving inside a conductor and what is happening. This is clear, I hope. So in conductors, free electrons, these are free electrons. These free electrons helps in current conduction. So these free electrons helps in current conduction inside a conductor. So this is clear. Next we are going to understand whether the current is a scalar quantity or not, or whether it is a vector quantity. So whether current is a scalar quantity or vector quantity. So vector quantities are those physical quantities that has both magnitude as well as direction. So yes, you are going to say current must be a vector quantity, right? Why? Because current has both magnitude and direction. You are going to say like that. But no, current is scalar quantity. Yes, current is scalar quantity. Why? I am going to give you some reasons. Why current is scalar quantity? See here what I have. This is a elastic rubber band. Just understand this as a conductor. This as a conductor, and electric charge is flowing through it. So ultimately electric current is flowing through it. So understand electric current is flowing through my left hand to my right hand. So understand electric current is flowing through my left hand to my right hand. So current is having a magnitude, that is true, there is no problem regarding it. But as well as current also has direction according to you. Yes, current is flowing from my left hand to right hand. Now current is flowing in a straight direction from left and right hand. But now if I bend this as like this, if I bend this rubber band or this conductor, say, which I have asked you to consider it as a conductor, if I bend it like this, then current is moving from my left hand to right hand here also. Now the direction has changed. Now the direction has changed. So ultimately it is quite clear that current doesn't have any direction of its own. The current moves in the direction in which the conductor is directed to, in which the conductor is placed. So current doesn't have any direction of its own. It moves in the direction of the conductor as it is placed in such a position. Current is scalar quantity. Current is scalar quantity because ordinary law of algebra is valid to add current. That is why it is scalar quantity. We can also say it like this. Suppose here is a conductor, another conductor, and there is a net joining of this conductor and current is flowing. So if 3 ampere is flowing through here and 7 ampere is flowing through this conductor, so ultimately 10 ampere is going to flow through this conductor. So just see here, I have done nothing. I have done simply addition, that is scalar addition. So ordinary law of algebra is being used to add currents in this circuit, right? So this is it. This leads to the concept that current must be a scalar quantity. Current must be scalar quantity. So in vector, what you used to do? You used to add vectors in vector algebraic method, right? So in current, no need to do such things. Current is a scalar quantity. We are safe. We are happy to use our own ordinary algebra as we have learned in our, I don't know in which class you have learned. Leave it. Just see what I have written. This is the famous celebrated Ohm's law. So this is Ohm's law. This famous celebrated Ohm's law on which entire electrical part is based on. Ohm's law. What it says? According to Ohm's law, current flowing through a conductor is directly proportional to the potential difference applied across its end, provided temperature and other physical quantities remain constant. So current moving through a conductor is directly proportional to the potential difference applied across its ends. That means, so if current moving through a conductor is proportional to the potential difference I have applied across its ends. If the potential difference is increased, the current is genuinely going to increase to the conductor if the physical quantities like temperature and other physical quantities remain constant. Here other physical quantities means length of the conductor or area of the cross section of the conductor or the temperature where you are keeping the conductor in the previous two experiments. So that is it is talking about other physical conditions. So V is equals to so V is proportional to I. So ultimately I can write, so V is equals to if I have to write any equals to sign, I have to put some proportionality constants. So R is the proportionality constant. So here R is the proportionality constant. So this proportionality constant is referred to as resistance. Resistance in the circuit. So what is resistance? Yes, I am going to let you know what is resistance. Resistance is nothing. Resistance is a general opposition that is offered or general hindrance offered to the circuit while the current moves through it. So when the current moves through the circuit, it is offered a hindrance. Hindrance means that is a slight opposition is experienced by the current, and that is called a resistance. So this is it. So this is the celebrated Ohm's law. I think you all know what is Ohm's law, and there is a famous graph also, Ohm's law. I am doing the graph in very small portion here. This is V and this is I. This is the IV graph. If V is increased, I increases. If V is increased, I increases. So we get V is equals to I. So see, this increases in the proportional way. So if V is increased, I increase in the proportional way. And to find this R, we have to find the slope of this line. Then only you are going to find out. You have to find the slope of this line. Then only you are going to find out this R from this curve. So this is it, the Ohm's law. If you have any problem, write me in the comment section, or you can also add me in Instagram. If you have any problem, you can text me in Instagram also. I am definitely going to reply you all. But before that, don't forget to subscribe this channel and like the video and press the bell icon. So you are going to get the notification as soon as I upload a new video. And if you really like the content of my channel, then please don't forget to share it with your friends and help your friends to succeed in physics. Help your friend to understand physics a little better. Thank you. So next we are going to understand what is resistance and resistivity of any conductor or any material. It is found that different conductors, that is different materials of same dimension, offers different resistance to the circuit. Suppose if you take a 5 meter long silver wire of whatever cross-sectional area, and if you take 5 meter long silver wire of same cross-sectional area, then you are going to observe that these two conductors are going to give different resistance to the circuit. Now same dimension, same cross-sectional area, still they are offering different resistance to the circuit. So which property determines which material will have more resistance compared to another? From here we need to understand what is this property which actually separates one material or one conductor to another, which make a difference between the resistance of the conductor. What it is? It is resistivity. So come, let us understand this part. So resistance of the conductor, depends on length of the resistance. If the length is very long, then the resistance offered is also very long. Suppose, just think of this, number of students, if they are asked to move through a small tunnel, through a long tunnel, very long tunnel, we are going to get irritated, right? If the tunnel is very long and we have to creep inside the tunnel for a very long time, we are going to be irritated. So that long tunnel is providing more irritation to us, that means more hindrance to us. Similarly, when the electric charges are need to flow through a very long conductor, its resistance increases. So resistance increases due to length. So we can say R is proportional to length of the conductor, right? Next you understand area. Now just think of this again. If many of you have been asked to move through a tunnel that is very broad. That is very broad. You can just move through it very freely. Now if you think you have to move through a very narrow conductor with very small cross-sectional area that is very narrow, you cannot move it through properly, then you are going to get irritated. Irritated means you are going to get more hindrance to move through that tunnel. So resistance is inversely proportional to area. That means if area is very large, if the area is very large, then it is very easy for the charge to flow. If the area is very small, it is difficult for the charge to flow. That means they get more hindrance. Think of the example I have just given you with this tunnel. Okay. So from here we can say this resistance is proportional to, so from here you can understand this resistance is proportional to L by A. Now it also depends on the material. It also depends on the material of the conductor used. So to understand this, we are going to understand that later. Okay, so here to move this proportionality sign, we need to put a constant sign. So we put here R is equals to rho L by. So what is rho? Here rho is a proportionality constant for a particular conductor. So rho is a proportionality constant for a particular conductor. So rho is a proportionality constant for a particular conductor. So from here it is clear that the resistance R is equals to rho L by A. Now for different material this rho will be different. That is a particular constant for a particular conductor. So what I was just saying, that resistance of a conductor is also depends on the material. So we can say the resistance of a conductor also depends on the material, and how it depends? It depends here as the rho. So different conductors have different resistivity. So here this rho is a proportionality constant, and also we are going to term it as resistivity. So rho is resistivity. So what is resistivity? Resistivity is the proportionality constant for a particular conductor. It actually defines which conductor will have more resistance or which conductor will have less resistance. So it actually defines or it actually gives the knowledge of the material used for the conductor. It is also said as specific resistance. So resistivity can be also said as specific resistance. So from here, from this equation, I have a small space over here. From this equation, we can also say rho can be written as R A by A. So unit of resistivity will be, this is ohm, area is here, meter square, and this is length. So if you put the units, you get ohm. This is meter square, and below here is meter. So if meter cancels, so we get ohm meter. So this is the resistivity. This is the unit of resistivity. We say it as ohm. We say it as ohm meter. Clear? So this is the resistivity, and this is how the resistance of a conductor depends on the circuit. This is clear to everyone? With resistance and resistivity, there comes another concept of conductance and conductivity. What is conductance? Conductance is with how much ease or how easily a current can pass through the circuit. So let us check the definition over here. So see here, conductance. So here with the conductance. The conductance of a conductor is the ease with which, ease means with how much easily it can pass. Okay. With electric charge flow, with which electric charge flow through it. It is a reciprocal of resistance. Reciprocal means the opposite. So unit is mho. We say it as MHO. So we pronounce it as mho. Okay. And conductance can be written as 1 by resistance. With conductor, another property comes the conductivity. How much conductivity of a conductor? Electrical conductivity, obviously. Not any other conductivity I am talking about over here. So conductivity of a conductor can be written as 1 by resistivity. So whatever the formula of resistivity, just the reciprocal of that will give you the conductivity. So conductivity can be written as 1 by resistivity. and unit of conductivity will be ohm inverse meter inverse. So this part is clear to everyone. Conductivity part was easy, right? It was easier. So now we are going to understand the vector form of Ohm's law, J equal to sigma E. This is new to you, I know, so check it out. So now we are going to understand what is the vector form of Ohm's law. So come, let us understand this part. Here we see a conductor. This is a conductor, okay? So I have applied a potential difference of V, and this is the length of the conductor. This is the length of the conductor, and electric current is flowing through this conductor. So resistance of the conductor will be R is equals to rho L by A, right? Resistance of the conductor will be R is equals to rho L by A. So here I can say rho can be written as 1 by sigma. Sigma means conductivity. I have just explained you what is conductivity. Opposite reciprocal of resistivity is conductivity, that is L by A. So this can be our equation 1. Now V is equals to IR. So let me put this R over here. So ultimately V can be written as I into L sigma A. We can write like this. Okay. Now we are going to see, if I bring this L over here, V by L, if I bring this L over here, we get 1 by sigma into I by A. Now V by L can be written as electric field, right? If you remember, or if you don't remember, I am there to make you remind. See, electric field was equals to minus dV by dr. Now this negative sign was signifying that electric potential decreases in the direction of electric field. That is very good. So here this is positive, this is negative, so potential decrease in this direction. So that means electric field is in this direction. So positive charge will be moved along the direction of electric field inside the conductor. Yes. Now some of my students will ask me, sir, you told in the chapter of electrostats that there is no electric field inside the conductor. Now how can you see there is electric field inside the conductor? Yes, my dear fellow, there is no electric field inside the conductor in static condition. That is, if you put some charge in the conductor, then it resides on the outside surface and there is no electric field inside the conductor. Now here this charge is flowing through the conductor and they are flowing, they are not static, they are in a state of flow. That means they are flowing, that means there must be some electric field, that's why they are moving in that direction of electric field. Positive charges and negative charges are moving in the opposite direction of electric field. So here electric field exists in this conductor in the direction in which positive charges are flowing, because here charges are flowing. If it has been in static position, no movement of charge, then there has to be that no movement of electric field, or there has to be considered that there is no electric field inside the conductor. Got it clear? If you have any confusion, comment section. So here E equals to dV by dr. Now this negative sign is to signify the electric field is in direction where electric potential decreases. So if we don't consider it now, that no need, we are just considering the magnitude over here. So E dr gets dV. So if we integrate, now dr is over here, for dr this total length will be this length of the conductor, E into length, and dV is the total change in potential difference between the across the conductor in these two lengths, right? This total conductor. So this is V. So electric field can be written as V by L. So here in case of V by L, I can write as electric field, and I by A, you don't know this term, I by A, this I by A is defined as J. This is known as current density. This is known as current density. This quantity I by A, current flowing per unit area at a certain position, is known as J, that is current density. So here I can write J by sigma. So here it can be ultimately written as J is equals to sigma E. J is equals to sigma E. Okay. So this is a form of another Ohm's law. This is called the vector form of Ohm's law. Why? Here J is a vector quantity and electric field is a vector quantity. Now I know there will be a question, sir, why J is a vector quantity? I will make another video for this. then why J is a vector quantity, just go to this link over there. Okay, I will make another video for this, and then there you will get to understand why we say J is a vector quantity. So here J is a vector quantity, electric field is a vector quantity, and sigma is a conductivity. So this is called the vector form of Ohm's law. This is called vector form of Ohm's law. Clear? So this part is clear. If you have any doubt, write me in the comment section. Now we have to understand how resistivity is dependent on temperature. If we increase the temperature of a ohmic conductor, then its resistivity increases. How? Take the example of it. Suppose you are moving through a very crowded platform, or you can say very crowded path. Okay, very crowded. Where as you are moving, you are getting collision with other people also. So this is very bad actually. This is so much crowded. Now if it is too hot, what happens? You will get irritated. You don't want to move like that, right? With each and every movement, you are going to push another person, you are going to push another person, quarrel with someone. So there is a hindrance in your pathway, right? Similarly, if you increase the temperature, what happens? Thermal agitation occurs in the conductor. Thermal agitation means the electrons, free electrons, strikes along with the flow, they also start to vibrate. That is thermal agitation. You have the idea of it, right? So due to thermal agitation, what happens? The resistance, what it was actually having, if there was no change in temperature, that is at zero temperature, it increases. So with increase in temperature, the resistivity also increases. So whatever the resistance was at 0 degree centigrade or 0 Kelvin, 0 Kelvin is very low. Whatever the temperature was at 0 degree centigrade, with increase in temperature, its resistivity goes on increasing. So we have to consider over here that resistivity, that is change in resistivity, is proportional to change in temperature, right? This is clear. So increasing temperature will result in increasing resistivity. Resistivity will increase. Another also, this change in resistivity along with the increase in temperature also depends on the initial resistivity. Suppose if a resistivity of a material is initially, that is at 0 degree, that is at 0 degree, somewhat say about 30 ohm per meter, just say, sorry, 30 ohm meter, just say. So if you increase the temperature, if you increase 10 degree, then how much resistance, how much resistivity will increase? And if you count, it entirely depends also upon the initial resistivity of that material. Got it? Just take an example of this. Just ask yourself, if you want to increase 10 marks, okay, from 85 to 95, if you want to increase 10 marks, how much effort you need to put? If I say how much effort you put will be reflected in your exam. To increase your marks in physics from 85 to 95, how much effort you need to put, and increase your marks from 65 to 75, how much effort you need to put. You are getting it right? So the amount of effort you need to put to increase your marks from 65 to 75, here also you have to increase 10 marks, and from 85 to 95, there also you have to increase 10 marks. So this difference of marks is 10, right? But the amount of effort you need to put totally depends also on, along with the difference of increase of marks you are doing, also depends on where was your initial marks, whether it is 65 or it is 85. Similarly, resistivity, the change in resistivity is also proportional. This change in resistivity is also proportional to the resistivity of that material at 0 degree temperature. So R naught equals to resistivity at 0 degree. Got it? This is clear. So on combining we get it is proportional to rho naught del T. To remove proportionality constant, we can say rho is equals to K rho del T. Here K is the constant, also known as coefficient of thermal resistance, thermal resistivity. Okay, here K is gone. Now what is this del rho? Del rho means change in temperature. Sorry, del rho means change in resistivity. So I can say resistivity as like change in resistivity at a certain temperature minus change in temperature minus resistivity at 0 degree temperature. This can be write down like this. Now on simplification we get rho plus k rho delta T. So on increasing temperature the resistivity increases. So how it increases? It increases in this form, and in this equation we can get how much resistivity increases. So this is clear to everyone. This is the temperature dependence of resistivity. So note it down. If you have any problem, write me in the comment section.